me left me this present. If it looks like it's yours, well, better yet, if it is yours, come get it. I already have a bunch of these. I got a lot of calculators, even those which cost $100. Students leave them, never come back to get them. Keys, nah. What do students come back to get? Cell phones. Got to have them damn cell phones so you can walk down the street talking to your neighbor who's walking down the street with a cell phone. 2 feet from you. Oh well. You know about this. I'll let you go to 11 o'clock. So for you early birds, you can count on having 2.5 hours if you need it. Room assignments, Turlington, L005, if your last name starts with A through J. On the other hand, if it starts K through Z, go to Turlington L011. That's tomorrow night. Now, some discussion classes didn't get this far, so to make sure everybody hears the same stuff, some comments, which again for some of you will be reviewed. First, about calculating the hydronium ion concentration for very dilute solutions. Now, the dilute solution could be of a strong acid, strong base, weak acid, weak base. The point to realize, if the solution is particularly dilute, you may well have to consider Kw, the autoionization of water, to calculate correctly the hydronium ion concentration for the solution in question. The example shown you in the notes is for that of 3 times 10 to the minus 8 molar hydrochloric acid solution. You know the solute ionizes 100%, so contributes a molarity, hydronium ion molarity of 3 times 10 to the minus 8 molar. But if you take that to be the hydronium ion molarity for the solution, since you know an acidic solution has got an acidic solute, right, HCl? It's got to be an acidic solution. So if you take 3 times 10 to the minus 8 molar to be the hydronium ion molarity for the solution, you'll be saying that an acidic solution is basic. Because an acidic solution cannot have a hydronium ion molarity less than 1 times 10 to the minus 7. Another example, 5 times 10 to the minus 8 molar sodium hydroxide solution. Here again, this solute contributes 5 times 10 to the minus 8 moles per liter of hydroxide ion to the solution. But this is a basic solute, so you know this solution is basic. It cannot have a hydroxide ion molarity less than 1 times 10 to the minus 7. So you cannot take this as the hydroxide ion molarity for the solution. That's absurd. But these are the kind of things that happen once you stop thinking about chemistry. And this is chemistry class. Chemistry is first and foremost. So, to exemplify the use of Kw, which applies to this solution, here's the Kw expression. Now, when water reacts with water in this solution, establishing this equilibrium with which we are now quite familiar, we can recognize that this autoionization reaction of water is the sole source of hydronium ion in the system. So we'll represent the hydronium ion molarity as X. But there are 2 sources of hydroxide ion. The solute, which puts in 5 times 10 to the minus 8 moles per liter of hydroxide ion, and this autoionization reaction, which puts in X moles per liter of hydroxide ion. So what's hydroxide ion for the solution? Add up the sources. X plus this. Oops. I had the HCl solution in my mind when I wrote this. So let me fix that data. Okay? Now, what do we do to solve this? First, forget quadratic recipes. That stamps on understanding chemistry. We don't want that. Second, the solution is quite dilute. That means for a basic solution, which this is, the hydronium ion concentration has still got to be close to 1 times 10 to minus 7. And for a very, very dilute acidic solution, the hydroxide ion concentration has got to be close to 1 times 10 to minus 7. Because the solution is quite dilute. It very much resembles pure water. So in solving, I'm going to speculate on an X value, which is close to 1 times 10 to minus 7. 8 times 10 to minus 8 molar does it. That's pretty close to 1 times 10 to minus 7. 8 times 10 to minus 8 molar is the hydronium ion concentration. If you put that in, you'll get 8 times 10 to minus 8 multiplied times 13 times 10 to minus 8. Then you have to do the real hard part. 8 times 13. And you find out the 3 sig figs, this gives 1.04 times 10 to minus 14. Well, to 2 sig figs, that's Kw, isn't it? So that's correct. Enough said. pH is 7.1. Slightly basic. Next. Again, some of you looked at this yesterday. But to be sure everybody has the same conversation shared with them, look please at page 1839 in the notes. So some of the comments I'm going to make will refer explicitly to the information which you have on page 1839. If you haven't yet read this page, read it. The discussion is about the degree or percent of ionization which can be achieved for a solute, a bronzostolaric acid or base solute, whose ability to ionize is governed by equilibrium control. That's a kind of a wordy way, but correct way, to refer to a weak acid or weak base. And you know how to identify those regarding the presence in our acid-base table. Well, we've recognized the more dilute the solution, the more you drive the ionizing solute to react with water. So the ionization extent increases as you increase dilution. But we're now going to look at this consideration in a more refined fashion than we have previously. The more refined aspect of this consideration hinges on the magnitude of Ka or Kb respectively. Because what you see on page 1839, which is discussed in detail for acetic acid and its conjugate base acetate ion, if Ka happens to be the unique value of 1 times 10 to minus 7, at infinite dilution, this acid solute will ionize to a max extent of 50%. Kb base, 1 times 10 to minus 7, ionization extent 50%. Which also means, I should say, if Ka is bigger than 1 times 10 to minus 7, then the ionization extent achievable by dilution exceeds 50%. But if Ka or Kb is smaller than 1 times 10 to minus 7, you cannot get to 50%. Again, the example given in the notes is for that of acetic acid, which has Ka 1.8 times 10 to minus 5, and acetate ion, the conjugate base of acetic acid, which has Kb 5.6 times 10 to minus 10. So acetic acid by dilution can ionize to an extent which is far greater than 50%. But acetate ion cannot even get close to 50%. The recipe for calculation of such is that perhaps you've recognized that this information, this recipe, which is derived on this page, is also provided to you on the information sheet. Again, I don't expect you to memorize this, but I do expect you to be able to use it. In order to use it properly, you need to understand it. And what we're talking about now is understanding this recipe, which again is derived on this page. Okay? For the acetic acid solution, as acetic acid ionizes, you're making hydronium ion and acetate ion. As acetate ion ionizes, you're making hydroxide ion and acetic acid. But since Ka acetic acid is a hell of a lot bigger than Kb for its conjugate base acetate ion, the acetate ion plus water reaction can never come close to 50% because that would involve building up a molarity of acetic acid which is greater than the molarity of acetate ion, and that ain't going to happen because acetic acid molecule is a much better H plus giver than acetate ion is an H plus snagger. That's what it amounts to. But conversely, for the ionization of acetic acid on reaction with water, you can build up a molarity of acetate ion which far exceeds the molarity of acetic acid. Again, because the ability of acetic acid to get rid of H plus far exceeds the ability of acetate ion to collect H plus. So, the other point of consequence regarding derivation of this recipe is to realize, as we commented about this solution, at infinite dilution, practically speaking, we're talking about pure water, aren't we? Let's take a swimming pool of deionized water and put in 1 molecule of acetic acid. Would you buy that as an example of infinitely dilute acetic acid solution? Sure. Well, in that system we just described, 1 molecule of acetic acid in an Olympic-sized swimming pool of deionized water. Do you think the acetic acid molecule, on a time average basis, will remain intact or will come apart and become, by reaction with water, hydronium ion and acetate ion? What will be the fate of that acetic acid molecule? React or stay intact? React. How about 1 acetate ion in the Olympic swimming pool? That does what? Does that come apart and become the acetic acid molecule? No! If you recognize the acetic acid molecule has got to come apart, then the acetate ion will not come apart. Because Ka acetic acid is a hell of a lot bigger than Kb acetate ion, isn't it? Because when acetate ion does its thing, it becomes acetic acid. And you just told me the acetic acid molecule is coming apart. That's correct. But the acetate ion won't come apart. Not on a time average basis. And at infinite dilution, since we're operating, practically speaking, in pure water, hydronium ion, hydroxide ion molarities are each 1.0 times 10 to minus 7. That's where this term in this expression comes from. Now, application of this term, question 1846. I think we asked you about a couple of acids or perhaps bases that are right from the table. Just take the Ka or Kb value for the base or acid or base considered and put them in. I think one of the things we asked you about was HOCl. Well, HOCl, Ka, let me dial it up. 2.9 times 10 to minus 8. I think I dialed it up correctly. Let me put in 2.9 times 10 to minus 8 here. And here you got 2.9 times 10 to minus 8 plus this. And from that you calculate max percent ionization of hypochlorous acid, HOCl, by dilution, as a function of dilution. But you already know before you do the arithmetic. Since Ka for that molecule is less than 1 times 10 to minus 7, the max percent ionization cannot be as great as 50%. It's about 29%. Now, 1847. First recognize that 1847 is not a trick question. It says 1847, the question. Is it possible that a Bl acid with a Ka value less than 1 times 10 to the minus 7 can ionize to an extent which exceeds 50%? Can a Bl base with a Kb less than 1 times 10 to the minus 7 ionize to an extent which is greater than 50%? Pardon? Yeah. You got to react it with something that's a better H plus grabber than water if you're trying to get that acid to react to an extent past 50%. And if it's the base with the Kb lowered 1 times 10 to the minus 7, you want it to react to an extent which exceeds 50%, you got to react it with a H plus giver that's better than water. That's all. Example, HCN. HCN in our table is found to have, let me see, a Ka value on the order of 10 to the minus 10. Why don't the first two numbers come to me? Let me see. Oh, well, forget it. Something on the order of 10 to the minus 10. It'll come to me if I think about it. That's not important. But, I mean, that means if I dilute HCN solution, I can never get HCN ionization extent to come close to 50%. Or the only thing with which the HCN can react is water. But if I put ammonia in the solution, that's a different ballgame. Now I write the reaction equation and recognize that just as we have done before, after we've written an acid-base reaction, if we find the reacting acid to be stronger than the product acid, or the reacting base to be stronger than the product base, the extent exceeds 50%. Let me see. 6.2 times 10 to the minus 10. That's Ka for this thing. Ka for this thing is 5.6 times 10 to the minus 10. Ah, I knew that table would come back. Okay. So, this is stronger acid than this. Not a whole lot stronger. So this goes greater than 50%. That's large extent. Anything bigger than 50% is arguably large extent. Tell me. Ka this, 6.2 times 10 to the minus 10. Ka this, 5.6 times 10 to the minus 10. Do you think then the extent of this, even though it's greater than 50%, is still not much greater than 50%? Does your horse sense tell you that, yeah, this reaction goes beyond 50% extent-wise, but not a whole lot beyond? Why? Do you find that these acids are very similar in strength? Their Ka values tell you that. Hey. So our horse sense should tell us, yeah, this goes past 50%, but not a whole lot greater than 50%. And soon you will recognize, if we make a mix, for example, of 1 molar HCN with 1 molar ammonia, you'll wind up with a solution for which the HCN equilibrium molarity will be a little bit less than 0.50. Equilibrium molarity of this will be a little bit less than 0.50. Equilibrium molarity of this will be a little bit greater than 0.50. A little bit greater than 0.50. And then we'll have the real fun question. This is at the end of chapter 18. We're not there yet. If I make this mix, how the hell do I calculate solution pH? That's fun. And in order to do that, we need one more consideration, which I reminded you about, but we're not there yet. And it won't be part of exam 1. Do you remember what this other part of the puzzle is? So we can take any water solution apart and analyze it in detail to the extent that pleases us to get molarities of all pH-dependent species. Remember what that other puzzle part is? Other consideration? It has to do with the kid running around the laboratory looking for the bottle of sodium ions. It's called charge balance. Electric balance. We're not there yet. Don't worry. We'll be there after exam 1. Which means I'll probably be talking about it on Friday. You better be here. I don't want none of this hangover stuff. It doesn't work in this gang. Every class is fun-filled. And if you miss the fun. And when you miss fun in this gathering, it causes bruises. I don't want you to get bruised. Do what I tell you to do. Then you'll do fine. And so we go to the remaining consideration, on which exam 1 depends. Our first look at hydronium ion concentration calculation for water solutions of polyprotic acids, of which there are 3 types. The parent acid is molecular and strong. The only common example is sulfuric acid molecule. And that's the only one we're going to look at today. The remaining types are, the parent acid is molecular, but weak, like H2S, or the real fun one is, the parent acid is still weak, but it's a hydrated metal ion, like hexaquo iron plus 3, which is a species whose formula you know appears in our acid-base table. So for exam 1, what we do now is part of exam 1. And we'll tackle this kind of stuff later. So the situation we're looking at now is the parent acid is molecular, sulfuric acid, and strong, which means when sulfuric acid molecules are dissolved in water, to what extent do they react with water? 100%. So that starts us on the chemistry. In preparing this solution, I've written the reaction equations with which we must be concerned to answer the question, what's the hydronium ion molarity for, say, this molarity of sulfuric acid solution? Okay? This goes 100%. That tells us that the hydronium ion molarity in a sulfuric acid solution is at least the numerical label on the bottle, M sub I. And not entirely, but quite likely greater than M sub I. Because this reaction, which involves the ionization of hydrogen sulfate ion, which is produced by this first reaction, given that Ka hydrogen sulfate ion is 1.2 times 10 to the minus 2. Remember what we just said over here about ionization extent? If Ka is bigger than 1 times 10 to the minus 7, then by dilution we can get this thing to ionize to extents which exceed 50%. Is 1.2 times 10 to the minus 7 bigger than 1 times 10 to the minus 7? I mean, is 1.2 times 10 to the minus 2 bigger than 1 times 10 to the minus 7?
Yes.
It's only 120,000 times bigger. So you'll find out that without making hydrogen sulfate ion too dilute, it will go 100%, at least within the boundary conditions of 2 sig figs. So we can well expect for this solution, before we do any calculation, the hydronium ion molarity is going to be closer to this number or twice this number. It's going to be closer to twice this number, isn't it? It shouldn't be quite as great as twice this number, but it might be. But certainly greater than this number. Because we've already paid attention to the chemistry of step 2. Ka for this, a big number as far as weak acids are concerned. And that's a fairly dilute solution. So we know this thing is going to go to a large extent, which will make, therefore, a substantial contribution to the resultant hydronium ion concentration. Okay? So that's what we concluded from reaction 1, and from 2, we now know that the hydronium ion molarity is M sub I plus what we get from reaction 2, which is the same as the sulfate ion molarity. Example. Let's imagine I start off with 100 of these molecules. Okay? After this first reaction goes, how many of these do I have left?
0.
After the first reaction goes, but not the second reaction, how many of these do I have? And how many of these do I have? Good. Now we're going to pay attention to the second reaction, because they are really occurring simultaneously. I start with 100 of these. To what extent or percent? Just for fun. Pick a percent. To what percent would you like to speculate step 2 goes? How much you want? 50%? Well, if it goes 50%, then this will become what? 50. This will become 50. Because you started with 100, 50 went away, so you got 50 left. And this will wind up as 150. What you got from the first step plus what you got from the second step. That's it. So from 2 we write, chemistry-wise, the hydronium ion molarity is M sub I, that's from the first step, plus sulfate ion. That's from the second step. Done. Now if you recognize that M sub I has got to be the sum of the molarities of hydrogen sulfate ion and sulfate ion, then it follows that this statement equals this statement. Because remember, after the first step, but before the second step, the hydrogen sulfate ion molarity is the same as M sub I, isn't it? Well, and by the second step, sum of M sub I, representing hydrogen sulfate ion, becomes sulfate ion. So M sub I is always going to be equal to hydrogen sulfate ion molarity plus sulfate ion molarity. Done. So that's how this is the same as that. So back to the solution we're operating on. Here's the setup, chemically speaking. Here's the setup, algebraically speaking. Now how do we want to solve it? You know how I solve these things and how you should solve them. What this answer, this hydronium ion molarity depends on, as it depends on for any sulfuric acid solution, is the extent or percent ionization of hydrogen sulfate ion. That's what it depends on. And of course M sub I. But the calculation aspect is about the percent or extent of ionization of hydrogen sulfate ion. So what percent or extent of ionization should I always consider first? 50%. Because if I start with 50%, try 50% HSO4 ionization extent. Or I write first, try 50% HSO4 minus ionization extent. Then the arithmetic is easy. Because at 50% ionization, this is half of this, isn't it? So what's this whole term become when I'm trying 50% ionization extent with this being the label on the bottle? What's it become? I'm listening. 0.015. Of course. This becomes 0.0005, and this becomes 0.0015. Here. And this is 0.005. So, at 50% ionization, this is what you got. All the time. All right? So you take half of M sub I, add it to M sub I, and that's your 50% value. Well, how does this compare to Ka? Ka is 1.2 times 10 to the minus 2. 0.0015 bigger or smaller than 1.2 times 10 to the minus 2. It's smaller. So the ionization extent must compare how to 50%? Got to be bigger. Because at 50% ionization extent, we get a term here which is smaller than Ka. So the numerator's got to get bigger while the denominator gets smaller. The ionization extent's got to be bigger than 50%. Well, now you know what to do. Let's see. I'll just write down that 87% is correct. You don't know how to play the game with your I'll let you use the pocket calculator now. You check the arithmetic, and you'll see that at 87% ionization extent, I get a value for this term, which is as close as it can possibly be to 1.2 times 10 to the minus 2. Enough said. Now, 2 more questions. Very concentrated solution, sulfuric acid. Say 6 molar, that's pretty concentrated. How will the hydronium ion molarity and sulfate ion molarities compare if the solution is very concentrated? Well, if the solution is very concentrated, the first reaction is still going 100%. But what about the extent of ionization for hydrogen sulfate ion in a very concentrated solution? Not very big, is it? This tells us that if the solution is very concentrated, the hydronium ion molarity will be about the same as the sulfate ion molarity, about double the sulfate ion molarity, or a hell of a lot bigger than the sulfate ion molarity. What is it? A hell of a lot bigger. Because that's going 100%, but the second one, which is the only source of sulfate ion, didn't go very far at all. I mean, if, for example, in 6 molar, the second reaction goes 1%. Well, by golly, then the hydronium ion molarity is 6, and the sulfate ion molarity is 0.1. I mean, 0.06, pardon me. 100% of 6 molar. Well, now, let's take a very dilute solution. Now, how does hydronium ion and sulfate ion molarities compare for our sulfuric acid solution? Very dilute solution. Look at the chemistry. That's where the answer lies. The first reaction always goes 100%. Very, very dilute. The second reaction, notice for 1,000th molar it went 87%. Well, let's take very, very dilute. Let's make it 10 to the minus 5 molar. What do you think is going to be the percent or extent of ionization of hydrogen sulfate ion? Practically speaking, 100%? You betcha. So, if the label on the bottle is 1 times 10 to the minus 5 molar, then the hydronium ion molarity will be 2 times 10 to the minus 5 molar, won't it? And the sulfate ion molarity will be 1 times 10 to the minus 5 molar. That's it. In the very dilute solution, the hydronium ion molarity equals twice the sulfate ion molarity. So take note. If you deal with a chemistry student friend who claims, for example, that in a water solution of sulfuric acid, the hydronium ion concentration for the solution that he or she is thinking about is 1.5 times the sulfate ion concentration. You look at them and you say, it's impossible. Impossible. Because you understand the chemistry and they don't. All right, one calculation. Let's pick on hydronium ion molarity and sulfate ion molarity in this concentration ratio. Hydronium ion molarity is 4 sulfate ion molarities. How are we going to get the hydronium ion concentration for the solution? Now, you remember this? We've got those over there. I just rewrote them over here. Okay. What can I write in for this? 4 sulfate ions. I mean, a lot of times you folks have trouble with this. Because these formulas mystify you, and I'm sympathetic with that. If you write it X's and Y's, you won't have a problem with it. But I encourage you not to write in X's and Y's, because you're dealing with chemical materials. And if you keep the correct formulas going through your arithmetic, you'll always have the labels right. But if you write in X's and Y's, oh, I can do that. Well, what the hell? You just change it to sulfate ion or whatever. Okay? So what's M sub I in terms of sulfate ion? M sub I is 3 sulfate ions, right? Nothing fancy about this. Now let's put hydrogen sulfate ion in the pot. This is 3 sulfate ions. So for this solution, where the hydronium ion molarity is 4 times the sulfate ion molarity, what's the hydrogen sulfate ion molarity in terms of the sulfate ion molarity? Well, 3 sulfate ion molarities plus 1 sulfate ion molarity. 4 sulfate ion molarities is this plus 2 sulfate ion molarities. Bingo! Can you put this stuff into the Ka expression now and solve? Absolutely. I know. For a while you're going to be in shock, because I don't use X's and Y's. If I use X's and Y's, you say, oh, this is easy. And I say, to hell with X's and Y's. This is chemistry class. We're talking about sulfate ion molarities, and hydrogen sulfate ion molarities, and hydronium ion molarities. Keep those formulas in there, so you know what you're talking about at all stages of the game. And what you'll get here is the determination that the hydronium ion molarity is twice Ka, which is 2.4 times 10 to the minus 2. I mean, just look at this, if you don't believe me. Isn't this 4 sulfates? And this is what? This is 2 sulfates, isn't it? And now, when I've seen students get, what do I do now? Hey, I got sulfate here and there. That's what I do now. If I put in X, fine. I'll leave it sulfate ion. Oh, golly, sulfate ion. I don't know what to do with that. Never saw a sulfate ion in my life. But I know X. Like hell you do. Sulfate ion has far more meaning than X will ever have. Okay? So, you have seen here that Ka value is twice the sulfate ion molarity. Take it from there. That's it for exam 1. Have at it.